Okay, today we're going to start off by looking at set theory. Many of you have done some parts or have done this topic already. So it will just serve as review for those who have completed it already. Alright, now the first thing, what is a set? So we have a definition that a set is a collection of well-defined elements. All right. And as an example, we could talk about set M being the set of months in a year. And just to remind you, when we are talking about set theory and we are defining a set, we use capital letters to denote the set. So, as I have here, if we have M, set M is equal to, and here we have this symbol which is our, it's really called a brace, and together the first part, when we are speaking, set M, your equal sign is equal to, when we have the two braces starting and ending, the set of, and then whatever the statement that you have inside, whether it's a mathematical statement or a verbal statement as we have here. All right, this is just a descriptive set. We could list them all and we could talk about January, February, etc., March, and I think you get the idea, all the way down to December. Okay, so we have when we are listing the set, so this list, sometimes the list is called the roster method. All right. So we have a roster method of describing, or a listing method, and we also have up here what we had, what we have was a descriptive method. Okay. Of course, we will use these interchangeably as we go through. All right, so nothing new here. Let's continue. Now, in general, since we're in math class, we probably won't be encountering much of the months of the years and such descriptive things, etc. All right, so let's look a bit at some of the sets that we'll be talking about. We have to know the difference between what we call a finite set versus an infinite set. Now, if we look back at what we just saw with this set of the months of the year, that of course is a finite set. We can list, so in a finite set, you're able to list all elements, and there's an end to it. Now, in particular, I could ask, what is the number of elements So n number of elements in set M. So we're just trying to get the notation down. Or another way of you sometimes hear or see the word, the cardinality. Cardinality of set M. Right. As we go through, I will probably more than likely use the simpler language rather than the cardinality, but be aware that you can see either words. So if we go back to set M, which was the months of the year, well, we all know that based on this list, we have 12 months or 12 elements. On the other hand, if we are looking at an infinite set, it would be impossible to list all the elements, right? So an infinite set, right, well, has an infinite number of elements or terms, number of. And already you probably know quite a few sets. If I look at the set of counting numbers, counting or natural numbers, then we all know that this starts from 1, 2, 3. There's a fixed pattern, it keeps going up by 1, but I can't list. If I ever think that I have gotten to the end, someone will just add another term, and so later on we can say that this is an infinite sum. Right now we'll just list this as infinity, although later on we will learn, well, maybe not in this course, but later on you'll learn that there are different types of infinity. So you'll have countable infinity and a bit more uncountable. So, all right. So those are finite and infinite sets. Before we go too much further, since I've already mentioned it here in terms of the counting numbers, let us use this time to look and review and see that we remember all of the number systems. So, number systems. We will talk about the natural numbers, and as we mentioned, or as I have said, the symbol given to it is capital N. I'll put that extra stroke in your textbook. It's always written in a bold letter, but can't quite do, or don't want to stop the pause to do bold. Let's look at this. 1, 2, 3, we notice that there's a consistent pattern. So I could say, well, if I think of the nth number in there, all I did was to find the next n plus 1, n plus 2. If I should choose to go in the previous one, then it would be n minus 1, going the opposite direction. All right? So we're seeing that, what we call the pattern. So as I go through, remember that mathematics is not just about solving equations or simplifying expressions. It's about looking at patterns. All right, let's go on to the next number system. Next number system is the whole numbers. symbol that we typically use for that is W, and the starting place is a bit different, 0, 1, 2, 3. However, if we look closely at the pattern, we'd have N choosing a number, let's say 23. How do I get to the next one? It would be add 1 to get 24 and so on. So N plus 1, N plus 2. It's the same pattern as the natural numbers, but just with a different starting point. If I should go in front, of course, then we would have N minus 1. Right? Okay, as we went on, so far, if we're looking at the development of our numbers, we sort of have this thing. So if initially we had 1, 2, 3, sort of your leapfrog and skipping stone kind of thing. So that was our natural numbers. Along came somebody, actually the East Indians, and they developed the number 0 and gave us our whole number system. The whole number, the 0, took 400 years to come and become a part of our lives, but that's a whole nother story. So as we go through, there is another development, and the development that we had was the use of the number system called integers. The integers, which we use the letter Z, because the German word for counting is Zahlen and so on. So that's where we get that letter Z from. And if I should ask, what are these integers? Well, we had no beginning, no end. The description of it was the whole numbers and their what we call additive inverses. Right? I'm sure many of you have forgotten what an additive inverse is, but never mind, we will see all of that as we review in the coming course. So if we have -3, -2, -1, 0, 1, 2, and so on. The difference here with the integers is that there was no start, there was no end. However, the pattern that we had seen of adding 1 as we go up the system still exists. And if I should even come before that nth term, I would have n minus 1, just as we had before. So again, the same pattern for consecutive integers as it is for consecutive whole numbers and natural numbers. All right, what is this additive inverse? So the additive inverse, inverse of A is -A. So if I have 1, it's opposite, going in the opposite direction, right? So would be one step from the from 0, but to the left. Likewise, for the opposite inverse or the additive inverse of 2 would be -2, and so forth. Okay. All right. So we end up now getting a number system that it's a bit like doing this leapfrog, but in either directions from the 0. Now, the next system that we can think of, or we go on to, is the rational number system. And the letter that is used for that is Q. And the set of rational numbers is the set, you'll most recognize this as your fractions. It's a set of fractions, or A is divided by B, and this double colon, or colon rather, it just means such that. So A and B are members or belongs to the integers, and we also have that B is not equal to 0. I'm sure you remember that if we divide by 0, that is called an indeterminate, or that's undefined, and later on we'll also talk about the indeterminate. Right? So A and B are members of the integers. So examples, you know, your usual 1/2, 2/3, 7/, -5, etc. Do remember that if we had, say, the whole number or natural number 2, this is the same as 2/1 or 4/2. So whole numbers, and as you can see here, are also belong to your set of integers. Now, we've gotten quite far in the development of numbers. Here we had our natural numbers, whole numbers, integers, and rational numbers. But as many of you dislike your fractions, you would prefer working in decimals. So we begin to, or in the development of math, we begin to ask, can all decimals be expressed as fractions? And the answer is no. So the only decimals that are rational, so decimals that are rational numbers are one of two cases. A, we would have those decimals that terminate. So for example, if you had 0.25, this is showing the 100th position, so it's really 25/100. Yes, I know you know that this should be a quarter, but then you would reduce and you have formed the fraction equivalent to your terminating decimal, a decimal that has an end. Now the second type of decimal that you have that is also a rational number are those that are non-terminating, but they're what we call recurring. So non-terminating, recurring, your favorite one is 0.33 or 0.3 bar. It doesn't matter how I write it. And this would be same as 1/3. We'll see later on how we get some of these, but if they are recurring decimals, then we're able to write them as rational numbers. So the question comes in, what else do we have? And we have irrational numbers. So the irrational numbers are not really a number system, but so irrational numbers, and we'll use the symbol Q complement. This means it is a set that is not a rational number. And examples of those would be things like pi, right? Pi is not 22/7, contrary to popular belief. You learn another interesting one called E for the exponential. Square root of 2, all those square roots that you didn't have a solution for, if you wish. Cube root of, say 4, cube root of 2, all the roots that you couldn't solve. Now if we express these as decimals, so irrational numbers as decimals, these will be non-terminating and non-recurrent. So there will not be a block of items or block that is can be put on the repeating bar. So an example, you might find this a little strange, but suppose we have 0.10, 100, 1000, 1, 2, 3, 4, 5. Yeah, okay. So despite the fact that this has a pattern, but it doesn't have there is no block, but no block of repeating digits or numbers. Right, so if I tried 0.10 or 10 and try to repeat it, the pattern has been broken. And no matter what I do here, there's no way that I can put this under a repeating bar. So this will be an example of an irrational number. If we go back to our little diagram, or jumping or skipping stones here, what's happening is that we now have, or as shown in the last picture here, we had our integers, -3, let me just put in a couple more, 6, 7. I know they're not evenly spaced, but that's okay. And when we look at what happens with the rational numbers are coming in and filling up the gap, right? So these fractions that you form in here are kind of closing this up. But if I am a very, very tiny mite or bacteria, I'm able to seep on through or get through those cracks. And what it turns out, the thing that fills those cracks, right, which would make it a nice solid line, is the irrational numbers. Right? So your irrational plus rational gives us a solid line. Nothing will fall through. And this is what we call the real number system. So our final thing is the real numbers, which we call R, and this is the set of rational, let's write it symbolically with a symbol that you've met elsewhere. The rational union the irrational, right? So it is both. Let me just go back a bit for those of you who may not remember all of your symbolism for set theory. Let's look at a simple or some simple diagrams, and then we'll go back to our number systems. So one of the things that we do is we'll have Venn diagrams, and in our Venn diagram, as we look at something pictorially, we might say that here we have the U is the universal set. It's a set of which everything that we're talking about belongs. And if we have a particular set, set A, then everything on the outside, so let's do this with an example. So let's pretend that we have the universal set, which is a set of digits. A set of digits is simply 0, 1, 2, 3. It's the first 10 whole numbers. Right? So in my particular case here, it's actually even a finite set. if I said that the set A is a set of even numbers, then here we would have 0, 2, 4, 6 and 2, 4, 6 and 8, and okay, so I could put these on my diagram, 2, 4, 6 and 8, and what else is left? Well, all of the odd numbers are on the outside. On the outside here, so it's not in set A, we use the symbol called the complement. So A and that strike is called the complement of set A, and it contains all the elements that are not in set A. All right. So in our case, this is just simply the odd numbers. Okay. All right. Now further, let's go back and look at some more notation, although I've used it on you. We have said that the symbol does look too much like an E. All right, this symbol means belongs to or is a member of. Right, so we could write this element 2 is a member of set A, 5 is a member of set A complement. Notice that 5 is not a member of set A. Alright, so do look back at some of those symbolism that you have met from previous classes. Alright, other symbolism. A subset. What is a subset? A subset, or we could say that set A is a subset of the universal set. It is, and there are several ways. A is a proper subset, or A is a subset of, this is an improper subset of or equal to a certain set. Alright, let's look at an example. Based on what we have done so far. So let us say that we are looking at a few sets. Let's set P, and since this is math class, let us start the process. And okay, so if I said the set of x's such that 5x is less than or equal to 16, x is a member of the, what do I want? Natural numbers. Okay. Let's see if we can look and see what we would get. So as we do in math, we would have worked this out. Divide throughout by 5. 16 divided by 5. We end up with x. X is less than or equal to 3.2. However, x is a member of the natural number system. If we list out or put in roster form what are the elements of set P, then they would be 1, 2, and 3. Let's go and do something similar. So another set, if I have set Q, and set Q is a set of x's. Sometimes I can write this a little bit differently, so I'll give you all the different forms. Set Q is a set of natural x's such that x is a natural number, and x squared is less than 20. So of course, solving this would be taking or trying to find all of the, or take the square root. There's no need to take the negative square root or negative values, because x is a member of the natural numbers. So square root of 20 would be roughly, this would be less than, less than 5, 4 point something, just as an estimation. And so if we were to look at this, then we would have the numbers 1, 2, 3, and 4. Okay. All right. So far we have set P, set Q, and if let's say that I want to bring up something else, PQR. If we look at set R, and I said that this is a set of x's such that x is a member of the whole number. Let's go back with the natural number system. Oops. Natural numbers, and x is less than 5. Well, this one's pretty simple. We again get 1, 2, 3, and 4. Taking a new set, set x is a member of the whole number system. If I have instead x is less than 4, or I'm making this up as I go along. So yes, x is less than 4, then I would have the whole numbers start at 0. So 0, 1, 2, and 3 is what we have. All right. Let's play with some of the number system again, just checking if, suppose we have set T. If I should ask for the set of whole numbers, and this time, again, I'm just really trying to see what you remember. So I'm bringing in some of those notation that you might have seen from your previous algebra class. So this reads that we have the set of x's. X is a member of the whole number such that x is between 1 and 5. Our x is greater than or equal to 1 but less than 5. So what we end up with is the answers or elements could be 1, 2, 3, and 4. All right, so using these, we're now going to talk about equivalent sets versus equal sets. So, what is two sets are equivalent. Right. So two sets, A and B, are equivalent if there is a 1-to-1 correspondence between the elements, between their elements. Okay, so if we look back, we had set Q, R, well, I have a lot of things. PQR, set P was 1, 2, 3. Let's look at set P, set Q, set R, and set S. Set P, set R, and set S. Okay. Did I copy these right? Of course not. All right, if we look at set P, if I try to put anything in one-to-one correspondence, I'd be missing an element. So what we can say is that set P is not equivalent to set R. Right? So P is not equivalent to R. However, I copied these down incorrectly. 0, 1, 2, 3. All right. However, if I looked at set R and set S, they are equivalent. So again, if I set up my equivalence relation or one-to-one, it doesn't matter how I do them, right? As long as I have an arrow from one element in each set, so I can conclude that R is equivalent to set S. Symbolically, R and the 3 horizontal lines, which would give us that equivalence, and so on. Now, especially when we have finite sets, so all of these were finite sets, then one of the things that we can do is we can say, well, if they are equivalent, then they must have the same number of terms. Right? Which is what we saw. The number of terms in set R was equal to the number of terms in set S, which was 4 terms in all. All right. Now, what's the difference between equivalent sets and equal sets? To be an equal, for two sets to be equal, two sets are equal if they have the same elements in each set. Okay. So one of the consequences is that yes, these sets are also, equal sets are equivalent. Right? But it doesn't go the opposite direction. So for example, going back to our many parts that we had up here, set P is not equivalent or equal to any of the other sets. However, set Q, set R, and set T are identical. They have the same elements, so they're all equal sets. But R, Q, and T are only equivalent to set S. Right? So S, going back here, S is equivalent to Q, which is equivalent to, well, I guess Q was actually equal to R, and R is equal to T. Okay. Right. In the same way, we could also say that the natural numbers, which were 1, 2, 3, this is an infinite set now, versus the whole numbers. These were equivalent sets. I could set them in a 1-to-1 ratio. Whatever n is there, then it would be, say, n minus 1 down here. And I could make up a formula that went with each, right? So we are able to do this. So set n is equivalent to set w, but set n is not equal to set w. All right, I think we have exhausted that a bit. You have also, let's look at the next thing. Okay, so we have looked at the symbolism for a subset. We've looked at an equal, equivalent sets. Let's do an example to ensure that we understand or remember the whole ideas behind a universal set, a subset or several subsets, and a complement. All right. So all right, let's look. So example, I guess two. Let the universal set. The universal set, we either will use the letter U or the E, the set of everything. And if let's do a mathematical problem. X, I'll give you a new way of writing something. Let's see if you understand it. So x is greater than or equal to 1, which is less than or equal to 20. X is a member of the positive integers, and set A is a set of x's such that x is a multiple of 2. And let's say B, x such that x is a multiple of 5. Alright. Now let's see if we understand this. So what we would do here is there would be 20 terms, 1, 2, 3, all the way up to 20. In the next one, listing the multiples of 2, there'd be your even numbers starting with 2, not from 0. 2, 4, 6, 8, 10. Should have all the way up to 20. And if I'm looking at multiples of 5, then this would be 5, 10, 15, and 20. All right. I check in if we understand or if we remembered some things. So having the universal set, set A is a subset of the universal set. It's a proper subset. It's not equal to it. If it's a proper subset, then there are less terms in that set than there's less terms in one set than the other. Right, so both set A and B are proper subsets of the universal set. You might remember we can diagram what's going on here by using a Venn diagram. So here's my set A, here's set B. What do they have in common? So numbers that are even and also multiples of 5. So we've completed all of set B, which was pretty easy. 2, 4, 6, 8, 12, I think my 14, 16, 18, okay. And on the outside, my universal set there, I would have had 1, 3, 5, no, sorry. 1, 3, 7, 9, 11, 13, 17, 19. All right. So we have here, I could ask, what is the complement of A? The complement of A are those terms such that X is not a member of A. Right? And if I look, then yes, that's exactly, well, if I look, then that would be all of, let's just shade it. It would be this part, everything outside of A. Okay. So we have all the numbers 1, 5, 15, along with everything on that outer edge. 1, 3, 5, 7, 9, 11, 13, 15, 17, and 19. Okay. All right. So we have the complement. And we understand that even this complement of A is a subset of the universal set, and so on. We can even see this portion, the set with 5 and 15, which we'll call and name shortly, is a subset of a complement. All right. Okay, let's look back at some things that you should remember in terms of your Venn diagram and intersection and union. All right. The intersection of two sets. Intersection of two sets, let's call it A intersected with B. Symbolically, we say that it's a set of x's such that x is a member of A and x is a member of set B. So it has to be a member of both. If we're looking at the union of two sets, so symbol is A and that U union B, set of x's such that x is a member of A or x is a member of B. And yeah, so x is a member of A or x is a member of B. So it belongs to one or the other. So consider, I don't want to make this example too hard. So if we consider these two examples, or rather a few. So let's take the universal set to be what? Let's take the universal set to be the digits, or 0, 1, 2, all the way up to 9. And let's take set A to be 3, 6, 9. Set B, what do I want? Let's take set B to be 2, 4, 6, and 8. Okay. So looking at this, I would be able to say what is common to both, what is the intersection of both. And the only term that we have is the element 6. If I, on the other hand, ask what is the union of the two sets, it's a joining of the two sets without repeating things. So although 6 is present in both sets, I'm not going to write it twice. And I'll actually, as I combine these two things, I will put it in order. Although that's not necessary, 2, 3, but it's just my preference, 6, 8, and 9. So we have those things. If I go back and look at the Venn diagram, I'll just draw two of them at the same time. So here is set A, set B. They have 6 in common, and 3, 6, 9, 2, 4, 6, 8, 0, 1, 5. Alright, so what elements are we missing? 0, 1, 5, 7. I think that's it. So let's just copy the same thing over here. 3 and 9. 2, 4, and 8. So if I asked what is A, or to shade A union B, or A intersect B and A union B on this side, then I'm sure we would agree that A intersect B is just this region, while A union B, which is what we have, in our listed terms here, and we would agree that those are the regions. So it brings up the question, how do we name the different parts of a Venn diagram? And that's what we will do in our next class. We will look at naming the various sections of a Venn diagram and identifying them, not only with when we have two sets, but extending that idea to 3 sets.